Hello, everyone. Can you hear me? Great. My name is Orson. I will be talking to you today about the new streaming engine that we built at Polars. Um, First, I want to layer it step by step. So I want to start with eager Polars. That's the kind of version of Polars that most people will use when they first start using Polars. Then when you get a bit more advanced, you switch over to lazy Polars, and I will tell you why that's better. Um, And then I'm going to talk about the two ways we can execute lazy polars in memory and now also streaming. So eager polars, I think if you're here and you're interested in polars, you've probably used it. I have a little example here on the left where we have a data frame. In fact, we have two data frames. We do a little join on the fruit column, but we're only interested in the green fruit. What percent for each sale? What was the percentage of the amount of money we made on that sale compared to the total? So a very simple query. When you write this in eager polars like this, it executes step by step. So exactly as you write it. I have labeled here 1, 2, 3. First, you do a join. Then the result of the join gets filtered, and then you add a column that's at the sales percentage. Each individual operation tends to be fairly fast when you use spoilers, but the overall computation as a whole, because you're not interested in intermediate steps, you're not printing the intermediate steps, you're not using the intermediate steps. The overall computation that you're interested in as a whole might not necessarily be efficient, and that's where lazy spoilers comes in. So when you add just a couple things to your query, you make your data frames, if they're in memory, you make them lazy, or if you're using file IO, you use read, you replace read with scan. I'm sure most of you have done that before. Polars will not execute each step by itself. It builds up a query plan for you in the background. And then only when asked, so when you either call collect or you use a sync method, it will actually execute the query that you're interested in. And this lets Polars optimize the entire query as one unit with full information. So how this works is that we take your query and we compile it to IR. We call it IR, intermediate representation. And I've just drawn that on the screen here with some nodes. So the circles, they are input data frames or input scans, and the square boxes are operations. So here, it's the exact same thing as you have on the left. It's just in a diagram matter, because once you are talking about the IR, you're talking about graphs. What we do with such a graph, once you actually collect the graph, is we optimize it. So in this very simple query example, we had a filter after the join. We were only interested in green fruit. But if we instead filter our fruit facts table to only include the green fruit, the join result will be much smaller. So the intermediate result gets a lot smaller. And maybe in this example, it doesn't matter that much, but in much bigger examples, it means instead of generating gigabytes of intermediate result, it might only be a couple megabytes of intermediate results. So it can make a huge difference. And in fact, when you so this is a kind of optimization. You could do this yourself. You could change if you go back to this little query that we write. Instead of putting this filter after the join, you could do this yourself. You could filter fruit facts by yourself. So this is not. It's nice that Polars does it, but it's not really mandatory or anything like that. But that changes once you start using smarter file formats. So for example, most of us have used Parquet before. If you haven't, you should check it out. Parquet can contain all kinds of metadata in the file format that lets the reader be much more efficient about which portions of the file it reads. So in this case, we add an extra filter to our example query. We are only interested in the stores in Amsterdam for our sales table. And we are using the scan Parquet. So we're directly reading from files, not from in-memory data. And what you can see is that once the optimizer is done with it, the filter is part of the parquet scan nodes. That means that the I/O reader, the thing that reads your data from disk, actually will only read the parts of the file, if possible. It's not always possible, but if possible, will only read the parts of the file that relate to the stores in Amsterdam. And that can mean if you have stores all over the world, that means you can be reading much, much less data. Your intermediate results get smaller and your computation runs a lot faster. So lazy polars, instead of executing step by step, it builds up a query plan. It actually does the execution when asked. And this lets us optimize with full information. So we can do less computation, the intermediate results get smaller, we can filter earlier, we can be cleverer, and most of that stuff you can do yourself, but we can also do more efficient I/O, which would otherwise be impossible. Right now, if you just call collect or sync on a lazy query plan, it executes using in-memory execution. This executes step by step. In the past, we've also referred to it as a tree walking engine. Nowadays, I think we've settled on the in-memory engine. We call it tree walking because we have our intermediate representation as a tree, and we just walk the tree. We execute each node of the tree step by step. So first we would read out all the stores in Amsterdam. Then we would read all the green fruit facts. Then we would do the full join on the data. And then we would have to do this sum and select, which it operates recursively. So you have the select node, and within the select node, you have these sub-expressions, and you would evaluate each sub-expression one by one until you have the final result. Each operator can therefore also see all data at once. This sum operator sees the entire data frame at the same time, so it can just perform the sum. We'll see later that this can be problematic. It can also be problematic because it can be very memory intensive. This join could massively blow up your data set. Like maybe not with the fruit facts if it's a one-to-one join, but if it's a one-to-many join or many-to-many join, it could create massive intermediate results. But in return, it is very flexible. Because every operator can see all the data at once, certain operations are very easy to implement at least, or could run very efficiently. Streaming execution. You don't have to change much. It's a new, fairly new parameter we added. We have this new engine parameter. You can just specify that you want to run on the streaming engine by adding it to your collect or to your sync argument. It uses the same lazy interface that you're used to, but it does an additional translation step. We saw that Polars translates your query into IR, and it does an intermediate translation step from IR again back to IR, but with more optimizations added. The streaming engine does an additional translation step. It goes from the IR to a streaming physical plan. This streaming physical plan will execute your query in phases. I'll show that in a bit. And during each phase, data flows through this computational graph in streams, which means instead of always having a full intermediate result at every step, data can flow through the graph without staying in memory if not necessary. So an example of this lowering to physical, to the physical plan, the reason that we need this is because in a streaming, when you're executing in a streaming way, you cannot see all the data at once. If you're computing a sum, you don't know what the result will be until you've seen every single input. You can only say what the sum was after that is done. So you need to have seen all data before you can continue. But another node in your query plan might not be. So we need to take those, they're sometimes referred to as pipeline blockers or for more technical terms, but you need to take out the parts of your query that you cannot run in a streaming way and turn those into dedicated nodes into your graph, and then have all the other nodes just be one-to-one, one input, one output. It gets more complicated than that, but we don't have forever here, so a simple example. So what we do here is we take out this sum, we make it an aggregate node, and we assign it a temporary column name. If once you start playing around with the engine, and we expose better ways to inspect the physical plan as well, because currently that's a bit complicated, you might see a lot of Polar's temporary variable names. That's not a bug. That's intentional. We have to make up new new variable names or new column names. We calculate the sum. We assign it to temporary, and then we recombine it with the original data to calculate the final result. If an operation, like for example a sum, is not a streaming operation, so that's something that we have to implement with a dedicated node in the streaming engine. Not every operation is supported yet in the streaming engine, and with the old streaming engine, the problem was if you hit one of those operations, it would just give you an error or run the entire thing on the in-memory engine. With the new streaming engine, if a part of the operation, of the part of your query graph is not supported yet, it will only run that part on the in-memory engine, and everything else, if possible, can still run in the streaming engine. So if you have a large query and only the final bit has some really weird function that's not supported yet, only that part will run on the in-memory engine. So here's the example of the three phases. A join, how it works internally, it builds a hash table or a dictionary for the Python folks, just a very much more efficient one. It builds that on one of the two sides. So in this case, data flows from the fruit facts per K file into the join operator. That's the first phase. Once that is done, once the join has seen all the data it needs to build the hash table, the second phase will start, and data will flow from the sales per K file already filtered on the store. It will perform the join with the fruit facts to create more data, and that might create a lot of data, but it will only be in very small incremental batches rather than one giant intermediate result. That will go into a multiplexer. The multiplexer is our general cop-out. Like data needs to go to multiple things. It needs to go to the left. It needs to go to the right. It tries to send it to both at once. If one of the two sides cannot yet proceed, so for example, you see, because I highlighted it in red, the zip cannot proceed because the sum is blocking. The sum cannot give out its sum before it's seen all the data, so that's blocking. So the multiplexer will have to buffer data in that case. So in this query, you will see that there will be some extra memory usage because it needs to keep the intermediate result around. In the future, we might also try to reduce the amount. If like in this particular example, I think it's probably a good idea. But in the future, if there's a multiplexer right before a file, we might choose to just split up and read the file twice, so it stays on disk. There's all kinds of interesting optimizations you can make to your plan in this way. But once the sum is done, once it has seen all the data, the multiplexer will flush its buffered data through to the end. So data flows, this is a bit more technical details for those who are interested. Data flows through the streaming engine in what we call streams. Streams are sequences of morsels, and morsels are essentially just a small data frame with a sequence ID. And the idea behind the sequence ID is because Polars is an ordered API, your columns always have an order, and you can execute expressions on columns separately and then put them in one select and they will line up, and that's because they're ordered. So we have to keep this track of this order in the streaming engine, so that's why each little data frame has a sequence ID that lets us reconstruct this order. Because nodes can connect to streams either serially or in parallel. And if a serial node connects to a parallel node, we do a distribute. If a parallel node connects to a serial node, we do a linearization. I think that's better viewed in a visual form. So an example of a fairly serial node is the head node. The head node just takes the first n rows of your output. And I mean, that's very much an ordered operation, at least in Polars. If you're interested in the first 10 rows of your data frame, it is important that you are actually getting the first 10 rows and not any 10 rows, assuming that the stuff before it was also ordered. If it was an unordered join, then we could be a bit more clever about it. But in this case, you only want the first 10 rows. So that has to happen in a serial way. So we see that there's a linearizer right before the head. But the filter and the select, they could run entirely in parallel. They are what we call element-wise, which means that every row can be evaluated independently from any other row. Well, the filter's not element-wise, but details. So those can run in parallel. And what we tend to do is every node, for the most part, does not actually implement parallelization itself. It just spawns a whole bunch of independent processing nodes, one for each core, that connect to each other. I don't know. I think it's best to just look at it visually. and the distributor distributes these morsels over your separate cores, and this leads to a rather robust parallelization. So in a nutshell, that is streaming polars. It gives you all the advantages of lazy polars. It modulo a bug here or there, it should all just work. Backwards compatible. It can handle much larger data sets. It depends a bit on the query. Some things are just inherently more memory intensive. Sometimes you just need to keep all the data in memory. In the future, we will be working on out-of-core support, which means that if you need to keep so much data in memory, you would run out of memory. It can start writing things to disk. That is not implemented yet, but that is on the roadmap. We definitely want to do that. And then you can handle truly much larger data sets. But already now it can handle, for most queries, can handle already a lot more data. The morsel-driven parallelism, that's what that's called, results in much more robust parallelization. So in memory polars, every single operation, whether that's a sum or a group by or any kind of select, it all needs to parallelize in its own way. It needs to do its own parallelization, but here you can just rely on the distributor and the linearizer, and for the most part, you'll get the parallelization for free with really good utilization of all your cores. It also leads to faster execution in different ways. Data stays in cache much more, but that's rather technical, so it's not the right talk for today. I do have a little bit of a benchmark for those who are interested. So this is PDSH, which is technically not TPCH, but it's very similar to TPCH if you're familiar with that. Running on a rather beefy Amazon machine, the C6A Metal. That's, I mean, you can see it on the screen, 192 core machines with 400 gigs of RAM. And this is doing a scale factor 100 benchmark, where one scale factor corresponds to roughly 1 gigabyte equivalent of CSV. It's stored in Parquet, so the actual data is a lot smaller because Parquet uses compression. But to give an idea of the size of the data, it's about 100 gigabytes if you used CSV to store it. And on this benchmark, the new streaming engine is, if you sum up all the times, it's around 3.5 times faster than the in-memory engine. Even though all the data fits in memory. So this machine has 400 gigabytes of RAM. All the queries, they fit in memory. It's not like it's swapping to disk. Despite that, it's still a lot faster. So even if you're thinking, oh, well, I don't have huge data sets that need a lot of memory, it can still be beneficial to use the new streaming engine instead of just in-memory polars. Lastly, we're hiring. So if you have strong Rust skills, and you're looking to join our team, you find the work that we do interesting, the URL's on the screen. See if we have a position for you that fits your interests. Thank you for your attention. If there are any questions, I'm happy to take them.
First of all, thank you. Interesting stuff. Can you say a little bit about the size of the morsel?
It's a very good question. So the question is, what is the size of the morsels? We have a parameter currently only exposed through an environment variable called polar's ideal morsel size. Uh, currently, it's hard coded to 100,000. Well, it's not hard coded. It reads the environment variable, but it's 100,000 rows. Uh, yes. That doesn't necessarily mean that it always splits in that. Like, if you get to the end of the file, it will split the remainder over however many cores you have. So it tries to distribute data over your cores. But this is not something we want to keep. We don't want to keep. This is just for simplicity. Ideally, we want the morsel size to be roughly like a third of your CPU cache in bytes. So all the data as it flows through the CPU, it stays in cache. Because if you have gigantic rows, you want to reduce the morsel size. If you have very small rows, like only 2 columns of like U8s, you want to use larger morsel sizes. We want to make it more dynamic, but currently it's 100,000 rows by default. Yeah. Any other questions?
Maybe tangentially related, but possible to build a static execution plan? Like how much overhead to get through, but how much overhead is building the query plan or the execution plan really take? Just make it possible to build that static for applying it to the same schema over and over again.
So if I understand, you have two questions. One is what is the overhead of the translation step from the IR to the physical plan, and second, can this be used for precompiled queries? Yes. So regarding the first, I don't know, but it's very small. The optimizer does a lot more work than the translation step that we do at the end. We will do a bit more work, but it's rather small. But it's also not zero. So if you have truly tiny data or you're doing like a lot of tiny things, you may just try it out and see how it is for your use case. It might be worth it to just use in-memory polars to not, or eager polars to not do this whole optimization step in query plan. Regarding precompiled query plans, I don't think it makes it easier or harder to do those. It's been a requested feature, but I don't know what the problem with that is that with sinks and sources, I guess you could somewhat do it, but if you collect into in-memory, it's not quite clear with the API model. We're working on it. It is a requested feature. Search the GitHub issue tracker and you'll find it. Any other? Oh, Richie in the back.
The static plan complicated if you add a file that has a different schema, then the whole plan.
Yeah, that's also a problem. So we read the schema from the files, and if the files change, the schema is incorrect. That's a complication as well. Yes.
Like reoptimization, for example, when you find out that you're joining, you go to the get and you find out the other side join information.
Yes. We do some in-flight optimization. For example, the join, it does a bit of a sample. It samples both sides. I think currently it's set to like 1 million rows. It will collect that from both sides in memory and then choose the smaller side if one of the sides was exhausted. If both sides are still full, because once you've got 1 million rows, you don't know. There could be like 1 billion more. It could be only one more. You don't have any idea. It will use a bit of cardinality estimation to pick a side. So we do that somewhat. We also do a bit of that with this phase system, especially when you get to much larger queries. It becomes kind of a hard problem to decide which part of the query are you going to execute next. Currently, it's very simple. The phase selection, it almost chooses one of the nodes that still needs to be doing at random, but the plan is to add more sophisticated scheduling also in the phases. Yes, but we don't do like full query recompilation. We don't do join order optimization, like only selecting a side of the join, but we don't like re-optimize join sides. Maybe in I don't know how many years, but it's a lot of work. It's very hard. Yes.
I was wondering, recently you guys collaborated with NVIDIA's Rapids team to create the GPU engine. Are there any plans to combine the power of GPU with this streaming engine?
I don't know. Maybe Gitchy knows. I don't know. I do believe they can substitute nodes, but I don't know.
I think NVIDIA wants me to answer this. So
Okay.
No, NVIDIA is interested in developing their own streaming engine for Polars because they have a lot of new GPUs which are effectively multiple GPUs on a single machine. I am not an expert on this, but as I understand it, they need to have some sort of streaming implementation to make it work on those hardware machines, and they are currently working on this. And they like the Polars model because they get a lot of information from us. So they get the whole IR from us, and they don't have to do any optimization, and they don't have to evaluate Python to understand what the user intends. So they get the IR from us, and they can just hand it over to the engine. So they are working on something, but we provide them the plan, and that's all we do on it. So yeah.
Yeah, I think in general the GPU engine we're rather hands off. That's mostly NVIDIA's doing. Yeah. Question in the back.
Linearizer has to work by buffering the chunks it gets and then get sorting by sequence number and then getting the next one.
Yeah, so how the linearizer works in a nutshell is it has a very small buffer per input head. And it will receive at least one morsel from each input. And once it has at least one morsel of each input, it can send through the morsel with the lowest sequence ID. It can send that through to its output and then continue at infinitum. So does that answer your question? I guess.
Yeah, because I was guessing also eventually it might need a whole bunch of memory. I guess you just block.
Yeah, you block. It provides back pressure. It has led to deadlocks. It is tricky, but it works once everything cooperates. So we use cooperative scheduling. We are built on async, Rust's async. I'm probably going to give a talk somewhere at some point, going more into the technical details on how it works. But it all uses cooperative scheduling, and the linearizer is cooperatively scheduled with the other nodes feeding it. Sorry.
How do you handle errors? Do you have like retry logic, recovery?
No. This is it's just like when you do lazy polars. If there's an error, it will bubble up and you'll get an error out, and it's exactly the same here. If one of the nodes has an error, it bubbles up. Everything else gets aborted, and there's no retry recovery. It's also this is all single mode.
If there's an error, there's a user error.
Yeah, if there's an error, there's a user error. So yeah. Question from the chat or?
Would the streaming engine be able to leverage Boolean like Partey statistics for optimization, for example,
I wouldn't necessarily say that's. I would say that's orthogonal to the streaming engine. Both the in-memory engine and the streaming engine could use those statistics. We wanna use those more. We do use them during scanning, but we don't necessarily use them a lot yet during planning. We do want to do that, but that's the IR optimizer, and that part is shared between both the in-memory and the streaming engine. There's no one final question.
This reminds me a lot. I'm old, so this reminds me a lot of Unix pipes shells. So I was wondering if Richie is planning to write a polar shell.
I don't know. Yeah, you have to ask Richie.
Sometimes
yeah. I do have to say I mostly designed this stuff. So if it's wrong, you can be angry at me, not at Richie. Oh, it's a thumbs up. Okay, yes. Thank you for your time, everyone.